learn by doing. Click on geometry, and we get this. There's three sections on the screen. There's x1, a point in space, x1, y1, z1, that we're going to leave at the origin, and then x2, y2, z2. That's going to be the extent of our antenna, the tip of our antenna. And that's pretty much all we're going to do there. And so to do that, let's go ahead and start the project by saying vertical. If I can spell, 20 meters. And we're going to go ahead and put it at the, just 14050, we drop down here. So we're going to be designing an antenna for the CW portion of the spectrum. There, hit return, and the program has said, okay, I've got 2 points. The beginning point is at the origin, and the ending point, x2, y2, z2, is also at the origin. Okay, let's go ahead and change that. We said that our model is going to be 5.1 meters tall. So, okay, so let's go over here and put 5.1 meters, enter, and that's it. We've just told the program the model that, the geometry of our antenna. Well, now we go to the View tab to make darn sure that what we told the program is what the program is drawing. So here, by holding the Shift key and moving the cursor down, we see exactly that, our antenna. You can go ahead and rotate it a little bit. In this particular design, it's fairly boring to be doing this, but when you have arrays of elements, this might come in handy. The other thing is we need to tell the program where to put our feed point. Now the program here is going to call it a source. So you notice the crosshairs right there. We're going to hover over the origin, right click, and say add source to the beginning of the wire. There you go. Let's go ahead and shift down right there. You notice right there that it's placed a little round circle right there, which is labeled here in the legend as the source. Next, we click on the calculate tab of the program. It's saying, we double check, it's saying I'm going to model for 14.05 megahertz, yes. What type of ground do you want to use? We're going to stay away from free space, perfect. Free space would be, if you're doing this in the space station, we're not doing that. Perfect, maybe over salt water, which is another topic, or real, that's what we're going to do. Okay, if we want real, what's our ground setup? Click on that, and you get these kind of things. The dielectric constant of the ground and the conductivity in millisiemens per meter, I believe it is. So, for example, it's now defaulting to average ground, okay? Not rocky, not very dry, not salt water. For example, for salt water, we would change this to 5,000 millisiemens per meter or something like that. We're not going to do that just yet. And for vertical antennas, we're going to do this click box right here and say, consider radials. Radials, we're going to go ahead and tell it they're going to be 11 radials, just to pick a number. Now, one thing to notice is we're not telling it the length of the radials. We're avoiding that conversation here. So it's nothing up the sleeves here, just being transparent. Now we say okay, and we are good there. Material, we're going to use, out of all these choices, we're going to select copper wire. It's aluminum wire, copper pipe, and all these things. Just make it simple, a wire antenna. And this is a vertical off of the ground, so we do not want it to be at a height of 1 meter. We're going to see 0. You can actually select it from the drop-down, or you can enter it directly. Now, we click Start, and that's it. That is the modeling of an antenna. What are we getting now? From the program, we're being told a lot of important information that's just come up on this line. One of them is the SWR of that geometry that you gave us, 5.1 meters, is going to be 1.58, which is not bad. Our resistance, our input resistance, 34.82 ohms. Again, not bad. Gain and all these kind of things we'll delve into here shortly. What I'm probably like you wanting to see is what's the pattern looking like. I'm a visual person, so we now click on far field plots. Click on far field plots and you get this. For those of us studying for our generals or our extras, this is OPAT, this is the azimuthal plot, and this is the elevation plot on the right. What I like to think of it as the azimuthal plot is this is like the antenna's in the middle there, and there's a crow flying right over, and our point of view is right as the crow's flying right over. Hey, it's overflying the center where an antenna is, and it keeps on overflying the antenna region. And over here on the right is the elevation plot. It's like you took a chainsaw to your azimuthal plot, and that's what you're getting right there. Well, that's great. Let's go ahead and do it in 3D. We can. 3D FF, fast Fourier, and then we get this kind of thing. Now you hold the mouse down, you go ahead and do that, you start seeing the pattern, which is a fairly boring donut pattern for this type of antenna. So I hope you've seen that in very few clicks we've been able to model a simple geometry, yes, but it gets better. One thing, if you follow Callum McCormick.
Quick question.
Go ahead, shoot.
How would it affect it if you took some of the radials out of it?
That's a very good question. Let me go ahead and go through all of these, and
Sure.
then at that point, you know what? We'll do the experiment that we put 11 radials and we got this. Now we can compare it in this program to 10, 15, n number of radials and see if actually how the pattern changes.
Okay.
That's the compare functionality. We'll delve to it at the end of the talk. But very good point. Okay, so the DX Commander, Callum McCormick, many of you, some of you might have heard of him. He has this criteria for a good DX antenna to be of an elevation of 5 degrees. He actually just recorded a video, or published a video yesterday about why this is important. And he goes back to an article by UCLA graduate Rudy Severance, I believe it is. Very, very sharp cookie. And he's got the arguments for actually keeping a 5 degree elevation and so on. And there's others. And anyway, so we'll use it as a given, so we'll say 5 degrees. And as soon as we tell the program 5 degree elevation angle, one thing has happened here. The azimuthal pattern has become smaller. Why? Because essentially what we're doing is we're taking a 5 degree cross section across this donut right here. So that is telling us, we hold the mouse down, and we see what our gain can be at this elevation. And you can watch Callum's videos of the X Commanders, and he'll make a very important point, which is when one buys an antenna, one can get, well, the gain is going to be 7 dB. Okay, great. But they may neglect to tell you at what elevation angle. And we've just seen that at this elevation angle is 6.3 dBi. We change the elevation angle to something else and it will be different. So this is important for what we want to do is DX. Okay, so that was that. We'll close MMANA GAL. You don't want to save anything. We'll go back to the top. Next practical exercise is, okay, we're going to model a 20-meter dipole antenna. Again, a bit of word about, this is the best sketch I could make, so please, apologies if it's not very clear. The thatched or hatched area at the very bottom is our ground plane. Now, what we have with the dipole is just a straight element of 5.1 meters in that direction from the source, and a 5.1 meter element on the 2 legs are 5.1 meters. Again, you can get that from an app or a website or something like that. How long do I have to make my antenna? The other thing we're not modeling right now is a coax, of course, or ladder line or anything like that. We're going to keep it simple. We're just going to see there's a displacement of 10 meters, say, and that's going to be our task. So let's model this antenna in MMANA GAL. We go over here, and we click on MMANA GAL, and the program launches. Program, by the way, is launching in the View tab. We click over here on Geometry, and we're back to our old friend here. We'll put in our name. This is going to be dipole, 20 meters. 20 meters. And we're going to again put in here, out of all of these, the 14.05, the CW portion. And here, as before, we click on the X1 cell, hit enter. Again, the program is telling us, okay, your 2 points to begin with are both going to be at the origin. Great. Here in this case, we're going to say, okay, the first leg is going to be minus 5.1 meters there, and that's going to be in the Y direction. And the second leg is going to be 5.1 meters there. Okay, fair enough. Nothing else. By the way, let me show you something real quick. We'll go to View first, and just like before, we can go ahead and twist this around and hold the shift key and move it up and down. We're gonna hover our cursor in the middle, right click, move source no longer to the beginning of the wire, but to the center of the wire. So right there we have modeled our antenna, okay? Now, by we're putting the source here, let me point you to, let's go back to the geometry tab and just in passing notice that the program has added this source right here. It's gonna be doing wire 1 in the center. It's gonna be applying a test voltage of 1. And in passing, we notice that we can use loads. Say, for example, we're trying to model a Wolf River coils or a super antenna. We can actually put inductive coils here. That's beyond the scope of what we're trying to do. Okay, view, again. View is always good, I find, to just double check that I'm not putting something totally wrong, or my X1 is here and diagonally I'm supposed to be. This is gonna be flat against the YZ plane here, as you can see, and there we are.
You're not putting the elevation?
That's a very good question, which is a good segue to the next step.
Okay.
Here's where we put the elevation, the 10 meters, right? So right here, we double check that the frequency is what we wanted. Yes, it is. Staying away from free space and perfect, we go to real, ground setup. I guess we can leave radials. I like to check it off. And then, again, just assuming the default, you can find this in the antenna book and in other places on the web, what dielectric constants and conductivities to use for very dry desert-like surfaces, seawater, fresh water, and things like this. So that's where we can get these things. But for now, we just use the default. Material, again, is gonna be copper wire. And here's the question of the gentleman in the back of the room asked. This is where we're gonna tell it. We're gonna be able to hoist it, so we're gonna hoist it 33.1 feet off the ground. That's 10 meters off the ground. Again, we hit start. Okay, just by that, we've actually come up with a 2.15 SWR 50. This 50 is gonna come important in the final practical exercise we're gonna do here. And then our resistance, our input impedance, 72 ohms, not bad. Gain, very optimistic at 6.75. So fine, let's look now at our far-field plots. Now we're starting to get a little bean or a potato looking plot here, and it looks like this. Again, what we can see is if we hold the mouse down, we start seeing right here the gain. The gain is being shown right up here. I didn't mention it in the previous, in the vertical example, but the gain is shown up here. It's showing 6.8, and fine. Again, we use the Callan criteria of using 5 degrees of elevation. Again, we want to make a DX antenna, see how good this would be for DX. And again, you notice that your potato plot there, or your bean plot just sort of shrunk. Why? Because he is concentrating only on the 5-degree cross section right here of your elevation. Okay, now what's about our gain? Well, our gain is minus 4.1. It was in passing, but in the vertical antenna that we modeled before with 11 radials, it was showing us at 5 degrees like a minus 6 point something dBi. As Callan McCormick mentioned, let's not get hung up so much on the actual magnitude of the gain in dBi. It's comparative, it's relative. He calls them bananas, okay? So minus 4.1 bananas compared to minus 6.1 bananas. Okay, and again, we're visual people. Let's look at the 3D plot. And now we're starting to see some insight there. That's our typical dipole plot. We can, at this point now, change all these parameters. So we can say, okay, what if I elevate it even higher? And I'm going on a limb here for this. I haven't rehearsed this, but let's give it, say we're lucky enough to put it 90 feet up in the air. If we say start, and we do far field plots, you start seeing, just like what the ARRL training manuals tell you, you start seeing these lobes coming out, okay, or other antenna references will show. So, okay, so we'll stay away from that one and we'll go into the next practical exercise. We can come back to it. And now we go to practical exercise number 3, which is going to be the final one that we do. And this one is going to be the most challenging. but I'm really taken, as maybe some of you are, with an antenna called the end-fed half-wave. It seems to have gotten a lot of press here in the last year, at least to me, and that's what we're gonna do. We're gonna model an end-fed half-wave antenna. The Brazos Valley Amateur Radio Club during field day activities this past year, 2023, had a practical exercise in which we actually built end-fed half-wave, the 49-to-1 transformer, which is at the core of the end-fed half-wave antenna. That 49-to-1 transformer is right here, is this box right here. This fellow right here. Let me show it to you. Okay, the ground, again, is gonna be the hatched area down at the very bottom. This is the best I could do in PowerPoint of a tree, so that's the trunk and that's the leaves up there. That trapezoid over there is going to be the 49-to-1 transformer of the end-fed half-wave antenna. That's going to be a little pigtail, which is going to be really the coax that I'm using in feeding my antenna. Or you can actually have a little counterpoise connected to the antenna. And the 67-foot wire line is going to be this one right here. We're going to drive the antenna at this point here. That's going to be the feed point. Okay, so if it's 67 feet, which is what we did in the exercise for the building of the antenna, what would I have to have as my X displacement, and what would I have to have as my Z displacement? Either trigonometry or Pythagoras comes to the rescue, and we come up with these numbers. Make this one 17.68 meters, and make the delta Z, the change in displacement in the Z direction, 10.218 meters. Okay? So let's get to work. Let's do that in MMANA GAL. I have to start. So we're on purpose starting from zero by launching the program, just to see that it's once you do one, two of these, it's yeah, I know what you're going to do. It's rote, right? So we go to the geometry tab. And here what we're going to do is we're going to title this fellow and fit halfway. Okay? And this time we're going to try something a bit close to the edge. We're going to go ahead and say, we've done 20-meter modeling, so let's try the 15-meter CW portion. So we'll do it for 21 meters. I'm sorry, 21.050 megahertz. We do that. And if you remember, we leave the origin, we leave the 0, 0, 0, the X1, Y1, Z1 at the origin. That's our origin. And we're going to have a wire sticking out to whatever those values were. Oh, let's see what they are. There. So it's going to be a displacement in X of 17.68 meters and a displacement in Z of 10.21. So let's plug those values in. Leave X1, Y1, Z1, 0. X2, now we're going to put 17.68 meters. On the Z2, we're going to put 10.218 meters. And that's it. Okay, so we just modeled our antenna. Let's look always at view to make darn sure that we're not doing something hallucinogenic. So we'll do that. Scroll down. And I'm having to hold my tongue right. But it seems to be against the XZ plane. So it's modeled what we're trying to model.
So the X would be the run on the ground?
Correct.
Okay.
Correct. Correct. And that's what I'm trying to simulate here.
Mhm.
What I tested something like this at Brazos Valley State Park, and essentially this was actually tethered with a buoyancy cord or whatever to one of the picnic tables, and then the cable extended over there to one of the trees. And what I'm using now is, since I don't want to really mess with the trees at the state parks, it's just a personal idiosyncrasy, I'm using the DX Commander fiberglass pole and just tethering the end of my antenna there and laying the pole against the tree. That actually came from K8MRD, a YouTuber. Mike was in Michigan, is now in Texas, again for us.
He's here today.
Yeah, he's here. So he came across with that, so that's helped out. Especially when one does activations of parks in the air, for example, on state parks in West Texas or Central Texas, where we don't have the trees that we're so lucky with over here. Right, enough blah, blah, blah. Calculate it. How do we do this? Frequency, 21.050, right? Ground. No radials really, leave the defaults, we'll leave that alone. At height, okay, now, in our model, if you remember over here, we had a displacement of about 3.3 feet. Why 3.3? Because that is 1 meter. So we're gonna have a 1 meter displacement, it's about yay tall, and from here, we're gonna go straight out to the tree. So that's what we're gonna model. Here, we're gonna say height. Now, if we try to select it from a drop down, there is no one meter, so we'll just enter it. Again, you can enter it or select it. And the material is going to be copper wire. Now remember, this is a little bit of the advanced part of the exercise. So one thing we noticed is the start button is grayed out. Okay, well why? Well, because I was not careful enough to go methodical. So if you click on view, we never told the program where the source, where our feed point is going to be. So he's saying to model what? You haven't told me where you're going to be feeding this thing. So we hover over the origin, right click, add source, beginning of wire, and there's our frame here. Little circle right there is the source. We go to calculate, voila, start is available. So we click on start, and we got terrible SWR.
In case you guys weren't aware,
Okay, so what gives, right? Well,
guys, so when I go to it,
we're telling it to go ahead and model this thing for a 50 ohm input impedance. But remember, we have a 49-to-1 transformer. 49 times 50 is a number called 2450. So let's go up to setup, and we see over here that the standard impedance is set to 50 ohms. So let's change that to 2450, 2450 ohms. Again, just to restate, we're changing this to 2450 ohms because the input impedance of this wire that's going to be radiating is going to be, due to the 49-to-1 transformer, is going to be 2450. Remember, the 49-to-1 transformer is going to get us down to 50 ohms, and that's going to be our coax.
So we're expressing the impedance of the feed point here,
Yes.
and it just implies there is a transformation required to get down to 50.
Right. Yeah, that's exactly right. The other way to do it is to actually add a load at the beginning, but I gave up on that. So this seems okay. Just my 49-to-1 is going to get me down to 50 ohms. So just do the modeling, assuming you're shooting for 2450. Nice thing about the program, it says now, if you notice, SWR 2450. So it was SWR 50, now it's changed to that. Now, without changing anything, we say start. Okay, actually that's what it was, 574. So that's not so good. I mean, it's better than 29,000, but it's still lousy, right? So let's go back to geometry. And now let's go ahead and say, remember we hear about adding the pigtail. Okay, my pigtail, okay, or my counterpoise, go ahead and add that baby. And let's say the origin is going to be the origin, but x2, I'm going to put it at -2 meters. Why? I don't know, like a 6-foot coax. The sheath of the coax is going to be my pigtail. Now, I go to view, always go to view, it's always a good practice. And I find it that, just to make darn sure I haven't done something silly. No, it's collinear, it's on the XZ plane, and there's my little pigtail here, he's fine. Calculate, leave everything the same, click start. Okay, now this we can actually, feel better about, 2.97. Still not the best, but good. Okay, go for it.
I've got a question. So that counterpoise you have on there is the shield on the coax.
That is.
But the coax isn't gonna be 2 meters. How
Well,
do you?
it's 6 feet.
Okay, so you're just gonna have okay.
I'm gonna have a 6-foot.
Yeah.
But hold on to that thought,
Okay.
because we're about to do something that's
Sorry.
very useful. No, it's good, please.
May I interject here?
No,
Just,
please.
What I've learned through trial and error is 13.5 feet from my transformer, I have 6 31 mix snap-on toroids. And that solved my problem by not using the model, by just trial and error.
How many feet? 13?
13.5 feet.
13.5 divided by 3.2808, 4.1 meters. Hold on to that number, because we're gonna do a feature of this program that I think you'll find useful, and it's something called optimization. Optimization is gonna say, well, it's gonna do that. It's actually gonna optimize, it's gonna come up with a statistical, mathematical way of actually saying, this is probably what you wanna be using. Let me show you. So if we click on optimization, we're gonna come up with this diagram. It's a little bit intimidating at first, but it divided into 2 parts. The sliders up here are what we're gonna be telling the program to optimize. And this area right here is what we're gonna tell the program, tweak this to get that optimization done, okay? So, the sliders go from left to right, so if you slide this gain down to farther left extreme, that's 0. Do not optimize gain. Front to back ratio, do not optimize it. Elevation, do not optimize it. JX, don't optimize it. SWR, I want that one optimized, push it over to the right. Match, I want that one optimized, move it over to the right, okay? Now, remember, this part right here was where we're gonna tell it what the program can tweak for us. We click here, and we get a bunch of options. Particular interest, you see wire, that's the one we're gonna select. And we're gonna select wire. Well, we have 2 wires. The program thinks 67-foot wire, the main one, that's wire number 1, and the little 2-meter pigtail. So let's try to optimize the pigtail first. Put that 2, do that, and then what out of wire 2 do you want to optimize? Okay, here we can say X2. Remember, X2 was minus 2 meters for the pigtail. So we click that, and the program says, hey, you've got that one set at minus 2. If you click start right now, he's going to optimize from minus 2 kilometers to plus 2 kilometers. So we don't want the max. I don't want it to go bigger than 0. The minimum, I don't know, minus 50 meters or something like that. In other words, go in the negative direction from 0 to minus 50 meters. See how that works. Let's give it a shot. Okay, the program is running. The program is done. Not what we wanted, 3.02, right? It's gotten a bit worse SWR, but notice the resistance, the input impedance is improved a little. We want this one to be about 24 feet. To the gentleman's point over here, we go back to geometry, notice what it's done. When we calculated his rule of thumb was 13.5 feet, which was 4.1 meters. The program, just from the limited information we put in, saying, hey, you might want to make that a bit longer than 6 feet. 3.83 meters, and not, instead of 2 meters, 3.83 meters, which comes out to about 11 feet, something like that. So use that in your cars, essentially. So, okay, great. I'm still not satisfied. That's still not good. Okay, let's go back to our friend optimization. And now what we're going to do is we're going to optimize the main element, the 67-footer. Okay? How do we do that? Again, click here and say wire. We're going to optimize one of the parameters of the wire. Might as well add another element of the wire here. Wire 1 is there, position 1. And what are we going to optimize? We're going to optimize X2. As the gentleman said, X2 is the displacement in the run, is what he called it, in the X direction. So that's what we're going to say. As soon as we put X2 here, notice that he remembers and he says, hey, right now it's at 17.68. It's a good quick check, and we're not in the wrong place. The second one is Z2. That one. And he's reminding us, hey, you've got that one set at 10.218. Fine. Again, it's going from minus 2 kilometers. Let's just put some sensible values. Go from 0 to 50 meters. And we're going to go from 0. We have to hit enter. I keep hitting tab there. It doesn't take it. So it's 50. Do that. And again, we're optimizing SWR and match. We're desensitizing all of the other parameters. We don't want the mathematical exercise. We want it to tell us this, SWR and match. Click start. The program runs. Now, when we say the program runs, that's fairly cocky, because this is a pretty amazing bit of software. I mean, we went back to those folks in San Diego that were modeling these things with enormous bits of hardware. I mean, the fact that with a computer, the laptop nowadays, we can just say, oh, we just did it right there, and here's your answer. Imagine these folks used to have to move that crane or that aircraft carrier model azimuthally to do this modeling and take days. Okay, so what do we get now? Good news. We got SWR 2450 of 1.05 and our input impedance of 2443. So we should be pretty close to the mark. Well, are we? Let's see what it did to our geometry. Remember, when we tell it to optimize, it will actually change our geometry. Okay, he hasn't touched our wire 2. Good. And remember, X2 was 17.68. Now he's telling us, hey, the math works better if it's 17.98. And what about your Z? Remember, the Z was 10.218. Now it's saying, hey, the math will work better if it's 10.718. Okay? So in a nutshell, it's telling us, hey, cut your antenna a little bit long. Don't cut it at 67 feet. Give us a little bit extra. And what we're going to do in the next part, by the way, this is going to be the end of this part of the talk, is we're going to actually build the thing and go out to a park and probably try it out. So the practical advice here is cut it long, and then you can tweak it with your VNA or whatever.
So, what's the second wire?
The second wire is a little, I'm calling it the pigtail.
Yeah, picked up, I mean, how many feet or meters is it?
Right. It's 3.81 meters. 3.81 times 3.2808 is 12.49, 12 and a half.
So did we calculate that as well, or
No,
where did that number come from?
right. Okay, it's this right here. So from our feed point up to this area, that's your 67 feet.
Yeah.
And off of the ground or something on the transformer right there, I think it's one of the legs, you actually just get a counterpoise, just a wire, like a radio.
So, but I mean, is it counterpoise that, did it change, or is it? Or
You changed it in the first part of the exercise, because.
That's what, I know that, but what is it now? Because you had two counterpoises, right?
No, one.
So you had one at the very beginning before you calculated
Yeah.
the length and.
We had it 2 meters, negative 2 meters, and then we did the optimizing of the counterpoise to see if we had it
So
right.
it's still using the optimized counterpoise?
Exactly,
Okay.
exactly. And
So is the question, does the length of the pigtail change as the frequency varies?
Well, we haven't changed the frequency. The frequency is still frozen at 21.050.
So like my 4.1 meters is optimized at 40 meters.
No, we're not talking about 40, it was 15 meters, the 15
Okay,
meter.
but the pigtail's shorter than the number I gave you.
It is indeed, it is indeed. Yeah, gentleman gave me 4.1 meters and the program said 3.8. I still think the program's pretty awesome for just very little information.
Well, but mine is optimized for 40 meters is what I'm telling you. Does the
Exactly.
pigtail length change with frequency?
That we'll have to try.
Okay.
I don't know. But and the other thing is we're glossing over a lot of points here. One of the things, for example, is a gentleman might be going ahead and using a very large gauge wire or a very thin gauge wire. The program here gives us that capability to enter the gauge of the wire here. We didn't tweak it, assuming 0.8 millimeter wire, whatever that AWG gauge comes out to be. But these things can change depending on gauge of wire, depending on obviously the frequency that we're going to try it out. And hold on to that thought. But going back to your comment, yeah, the first optimization gave us 3.81. We left it frozen. We didn't mess with it. But if you think about it, we told the optimization panel to consider this element right here. It changed this one for sure. But we told it, hey, you're free to change this one also. I mean, it was there.
So.
Before you leave the,
I was
sorry.
just gonna ask you, why didn't you change the long wire first? I mean, I know it's easier to change the counterpoise, but what would happen if you changed that one?
The answer to that one, I'm going to be very honest, because this is what I rehearsed for this presentation. Because if I start straying away
that's
from
fair.
these, I'm going to get in a bind.
Yeah,
And you're going to ask me a question, so I'm going to give you the deer in the headlights.
Can I ask you a question before you leave the gauge?
Sure.
Okay, so you're using LMR 400 or 213. That's due to the skin effect that is happening on the top of the wire. The gauge doesn't really, the coax would need to be, the gauge would have to consider the size of the coax. Would that be correct?
Yeah, I think, yeah, your point is, and I'm sorry about that, I was confusing there. I did mention AWG gauge, and by that I mean, yeah, we're modeling 0.8, millimeters. But I did also mention that for our pigtail, I was using, and that's what I've used in the parts, is actually the coax. And the outer sheath of the coax is exactly what you're pointing at, and you're spot on. The LMR 400 might be, different diameter than the RG8X or whatever, so it might be different. Characteristics are different. But with very basic, I hope you're taking this away from this talk, is very basic input parameters, very simple, you know, 1 tap, 2 tap, 3 tap, we get to this. So, and now one thing we haven't done with that our 1.05, 2443, it hasn't actually written, before we go to the far field plots, we have to start one more time to write it to the file. That's a little idiosyncrasy of the program. Once we do that, of course, that's the same thing as we just saw with the optimization. Click on far field, and now we get something interesting. This is the radiation pattern of an end-fed half wave for 15 meters, okay? So you start seeing your azimuthal plot on that side over there. It sort of looks like, you know, the two lobes. You're starting to see some directionality to it, yeah?
Which direction?
The orientation of the antenna,
Ah,
that always
thanks.
bothers me.
That was my question exactly.
Good question. Okay, let me cut to the chase. 3D fast Fourier is your answer. That one's going to show you that light blue line right in the middle there, starting from the origin and projecting outwards. That's your antenna right there. So if we turn it like so, the antenna is facing from the origin out, from the origin out, okay?
Okay, where is it on that other plot, the straight down plot over there that you got
Okay,
covered up?
missed that.
It goes left to right, right?
Well, it's positive X to negative X, I believe. Tell you what,
Which is the vertical axis.
it's,
There you go.
yeah, something like that.
Okay, so it's up and down.
So now, something interesting also is, again, we're wanting to design an antenna for DX, at least the exercise for my interest would be. So use the 5-degree elevation from Cowan, enter, and look, the pattern starts looking weird, looking different. Why? Because if you think about it, the antenna is coming out of here. No, it's okay. From here outward. So there, you're gonna be in between two lobes that are not very apparent on these two plots, but if you look at it on the 3D fast Fourier, you start seeing them right there. So there's this lobe and that lobe right there. And those are the ones that are protruding here. And then that one right there is the, away from the antenna is where you're getting a pretty good DX. Yes, sir?
5 minutes.
Okay. Okay, so anybody that's interested on this, we can always do it later, but let me go ahead and wrap it up right quick by showing you the last bit, which is going to be Whisper. I know we're sort of rushing through Whisper, and apologies for that, but hopefully you'll get the idea that Whisper is fairly straightforward, not complicated at all. Go ahead. All right, so Whisper, what I've got here is I've essentially just got a transceiver onto a dummy load, USB. So the only reason I have it there is just to show you what the Whisper program is actually doing. It's a beacon program, so you're not gonna do QSOs with it. The interface is extremely simple, believe me. And what you do is you have the choice of band right up here. There's a drop down here that will select the frequency for you. So you don't have to know that the Whisper frequency is this. You just select, you know, the 14 point something for the 20-meter band, and there you go. The other thing that you've got is you've got the different options over here, such as upload posts, upload spots. You can work not connected to the internet for Whisper, but if you want to report your spots, you want to click, you want to have connectivity, and you want to say upload spots. And the last thing in passing right here is these buttons right here are going to be your tune button, enable, which will get the program to actually transmit, and this selection right here, which is what power you're transmitting. Whisper requires you to go ahead and enter the power that you're transmitting in your transceiver. He doesn't read that from your transceiver, so you have to tell it. Why? So that you can report to WhisperNet, okay, what actually power you're using, okay? And the last one is band hopping. There's many videos on the internet, I encourage you to see those, and they will actually talk to you about, this will actually start probing different frequencies sequentially. Every 2 minutes it'll switch frequencies. So you'll actually get a propagation map pretty automatically, okay? So that's the last one. The only other thing that I alluded to briefly is once the data is uploaded, and it's being uploaded by multiple stations around the world, you get this kind of display. This is one of these freely available displays. These are all propagation plots, if you will, with Whisper. You can zero in on your station right here, for example. Notice there's one Whisper beacon station right down here. And yes, that is in Antarctica. That's the German Whisper station there. So you can actually, with 5 watts from, downtown Houston, essentially, you can actually propagate all the way out to Antarctica, to the German. They'll hear you. So, very interesting.
So what's that program there that you're using?
This one is called Whisper Live.
Okay.
Whisper, WSPR.live.
I've used WSJTX.
Well, the program is WSJTX.
Okay.
The dashboard is. So with that, I'm gonna have to field questions later. Sorry about the brevity.
Hey, great job.